The CLR execution process describes how a .NET application runs internally from the moment the program is started until it terminates. Although developers usually interact only with source code and output, a large number of complex steps occur behind the scenes. The Common Language Runtime (CLR) manages these steps to ensure that applications execute safely, efficiently, and consistently. Understanding the CLR execution process provides deep insight into how .NET applications work internally and explains many important concepts such as IL, JIT compilation, memory management, and runtime services. The execution process begins long before the first line of user code runs. When a developer builds a .NET application, the source code is compiled into intermediate language, IL, and metadata. This IL is platform independent and cannot be executed directly by the CPU. Instead, it must be processed by the CLR. The compiled output is packaged into an assembly, which contains IL code, metadata, and a manifest. This assembly becomes the input for the runtime execution process. When a user launches a .NET application, the operating system first loads the executable file into memory. The OS identifies the application as a managed executable by examining its header information. Instead of executing it directly, the OS transfers control to the CLR loader. At this point, the CLR takes full responsibility for managing the application lifecycle. The first major step in the CLR execution process is runtime initialization. The CLR initializes internal data structures required for execution. This includes setting up memory management systems, thread management components, exception handling infrastructure, and security mechanisms. The runtime also prepares internal tables used for type loading and method execution. Once initialization is complete, the CLR creates an application domain. An application domain is a logical isolation boundary within a process. Each application domain has its own configuration, loaded assemblies, and static data. This isolation improves stability by preventing one application from affecting another within the same process. After the application domain is created, the CLR begins loading assemblies. The assembly loader reads the application's manifest to identify dependencies. Based on this information, the runtime locates referenced assemblies from the application directory, shared locations, or configured paths. Each assembly is loaded only once into an application domain. During assembly loading, the CLR reads metadata from each assembly. Metadata describes types, methods, fields, and references. The runtime uses this information to understand how the application is structured. At this stage, only metadata is read. The actual code is not executed yet. After assemblies are loaded, the CLR performs verification. Verification ensures that IL code is type-safe and follows the rules defined by the common type system. This step prevents illegal operations such as accessing invalid memory or performing unsafe casts. Verification is one of the reasons managed code is considered secure and stable. Once verification is complete, the application is ready to execute managed code. The CLR locates the program's entry point, usually the main method. However, even at this stage, the IL code has not yet been converted into machine instructions. When the main method is invoked, the CLR checks whether native machine code already exists for that method. Since this is the first execution, no native code exists. The CLR therefore passes the IL code of the main method to the just-in-time JIT compiler. The JIT compiler is a critical component of the CLR execution process. It converts IL instructions into native machine code that can be executed by the CPU. This compilation occurs method by method. Only the methods that are actually executed are compiled. This improves startup performance and reduces unnecessary compilation. After JIT compilation, the native code is stored in memory. The CLR then transfers execution to the CPU, which executes the compiled instructions. From this point onward, the program begins performing its intended operations. As the program executes, new methods may be called. Each time a new method is invoked, the CLR checks whether that method has already been JIT compiled. If not, the JIT compiler is invoked again. This process continues throughout the application's lifetime. Modern versions of .NET use tiered compilation. Initially, methods are compiled quickly with minimal optimization. If a method is executed frequently, the runtime recompiles it later using advanced optimizations. This allows the CLR to balance fast startup with long-term performance. During execution, memory management is continuously handled by the CLR. When objects are created using the new keyword, memory is allocated on the managed heap. Developers do not manually free this memory. Instead, the garbage collector tracks object references. The garbage collector periodically runs to reclaim memory occupied by unreachable objects. It identifies live objects by scanning routes such as stack references, static fields, and CPU registers. Objects that are not reachable are considered garbage and are removed. The CLR uses a generational garbage collection model. Newly created objects are placed in Generation 0. Objects that survive collection are promoted to higher generations. This design improves performance because most objects are short-lived. During garbage collection, the CLR may also compact memory to reduce fragmentation. This improves memory efficiency and CPU cache performance. Stack management is another important part of execution. Each method call creates a stack frame containing local variables and parameters. When the method returns, the stack frame is automatically removed. This process is fast and does not involve garbage collection. Exception handling is tightly integrated into the execution process. When an exception occurs, the CLR stops normal execution and begins searching for an appropriate catch block. It walks up the call stack until a matching handler is found. If none exists, the application terminates gracefully. The CLR ensures proper stack unwinding during exceptions. This guarantees that finally blocks are executed and resources are released safely. Thread management is also handled by the CLR. Applications may create threads explicitly or use thread pool threads. The CLR manages scheduling, synchronization, and context switching. Asynchronous programming using async and await relies heavily on the CLR's task scheduling infrastructure. During execution, the CLR enforces type safety and access rules. It ensures that methods are called correctly, fields are accessed legally, and objects are used in accordance with their declared types. Security checks may also occur during execution. While modern .NET relies primarily on operating system security, the CLR still ensures that managed code does not violate runtime boundaries. Reflection and dynamic loading can occur at runtime. When assemblies are loaded dynamically, the CLR reads their manifests and metadata, verifies them, and integrates them into the execution environment safely. Throughout the execution process, the CLR monitors performance and execution behavior. This information is used for runtime optimizations, such as tiered compilation and memory tuning. When the application reaches the end of execution or is terminated, the CLR begins the shutdown process. It stops executing managed threads, runs finalizers if necessary, releases resources, and cleans up internal structures. Finally, control is returned to the operating system, and the process exits cleanly. The CLR execution process can be summarized as a continuous cycle of loading, verifying, compiling, executing, managing, and cleaning up code. Every stage is carefully controlled by the runtime to ensure reliability and efficiency. The greatest strength of the CLR execution process is abstraction. Developers are shielded from low-level concerns such as memory addresses, pointer arithmetic, and manual resource management. At the same time, the runtime delivers high performance through JIT compilation and optimization. Understanding the CLR execution process helps developers debug issues more effectively, write optimized code, and perform confidently in technical interviews. It explains why managed applications behave differently from native applications and how runtime services work behind the scenes. In conclusion, the CLR execution process is the backbone of the .NET runtime. From loading assemblies to executing native code, from memory management to exception handling, every aspect of application execution is governed by the CLR. This controlled execution model provides safety, flexibility, performance, and reliability. A strong understanding of this process completes the knowledge of CLR architecture and forms a solid foundation for mastering .NET internals.